Hello everyone, I'm Hussein and this is Hazem. And this is our advanced machine learning project. Uh, we're doing reinforcement learning for Minesweeper. Minesweeper is a classic game. The point of the game is you have a board. The board has hidden mines and you try to reveal all the cells that are not mines. The cells can have one of three states. They can be just empty, or they can have a number from 1 to 8 for representing that there's an adjacent mine, or it can be a mine. If the player steps on a mine, he loses. If he reveals everything other than the mines, he wins.
So we first proposed to develop a neural network that is based on Q-learning and specializes in experience replay and a deep Q architecture. So with the paper that we're following, we found that there's a current state of the art of 45% win rate.
We decided to build our own custom environment that is compatible with the Gymnasium library. Gymnasium library is a library that has a bunch of environments for reinforcement learning, including a lot of classic games on the Atari and everything, but they did not have an environment for Minesweeper. So we decided to use our own, but add functions so it functions the same as any environment in Gymnasium. This is our initialization function. It takes in the size and the number of mines. We chose a size of 9 by 9 and 10 mines, which is the easy difficulty in this game. Then we have what we call the real board and the agent board. The real board shows the representations of where the mines are and the adjacent cells. The agent board is the state that we, or observation that we give to the agent to train on when playing the game. Then we have function to add the mines and count the adjacent cells. Then we have our observation and action space. These are the ones that are needed for the gymnasium environment.
Okay, so the first function, which is add mines, randomly places the mines on the board, which are always donated by a -1. So we have the function that already iterates over each cell and makes sure that the cell does not already have a mine. Then we have the count adjacent, which counts like so it goes over every cell and checks whether there are mines in the adjacent cells, sums the count and just places it in that cell.
Then we have two other functions, reveal and no revealed neighbors. The first one, reveal, just reveals a cell and then recursively goes through the cells beside it, because if you reveal an empty cell and then there are more empty cells around it, usually in the classic version of the game, it reveals those cells too. And no revealed neighbors checks that a cell has zero revealed neighbors. We use it to check if the agent is taking a random guess.
So the next function, win, just does what it says, checks if the game is won or not. We also have reset, which is required, and it resets the environment after each episode when training the model.
The step function is another one of the required functions for the gymnasium environment. The step function is the heart of the agent's training. Uh, after the agent gives us an action, the step function takes in the action and converts it to a real action on our actual board, and then it calculates the reward based on what the agent did and updates the state and gives the reward and new state back to the agent.
Okay, so here we have a picture of the actual board with the numbers representing whether it's a mine or an empty cell or an actual number. So -1 is a mine, 0 and 8, 0 to 8 is for the number of adjacent mines. So for the agent, actually, they don't get this. They get the same board but filled with -2s, which are hidden in cells.
We decided we struggled a lot with building the environment, so we decided to use a DQN function that is already implemented in the standard baselines library to run or train our agent. The results were honestly not the best. The agent would keep getting stuck in weird negative loops, and at times the best score would be when the agent just loses the game as fast as possible to get a score of -10. Other times he would just keep making invalid and random guesses, never making correct moves, and this led to very negative rewards.
So for our proposed solution, we're changing, or we want to try and change the reward system. So it's actually based on the probability of the guess. So a higher probability guess would net a higher reward, and vice versa.
Our interesting findings is first, we had a lot of issues with building a compatible environment that could use other libraries for DQN or the Gymnasium environment library, which has a lot of integrations with other libraries, so we can run our model. After fixing that, we found that most DQN functions seem to just struggle to converge and get good results from our agent after trying multiple libraries. This is probably due to the nature of our problem. It has a big observation and action space. Most problems give very small action spaces. Like the classical games on Atari, their action spaces are very limited, like moving up and down, left and right. So we decided we will implement the DQN, the Deep Q Learning Network, from scratch, which would probably be best for our problem to yield good results. And we looked at multiple projects that had implementations of DQN, and we decided in the next steps we will do this.
So for the first step, we actually want to finish the algorithm to calculate the random guesses and the probabilities and actually try to integrate them within the agent reward system.
The next step will be writing the full implementation of the Deep Q network from scratch to make a very custom model architecture for our problem.
And the third step is to fine-tune our agent and customize our DQN model and try to optimize the results.
These are our contributions. I built the environment and worked on the algorithm to calculate the dynamic rewards.
And I worked on the DQN agent and evaluating and testing the policies and researching future DQN implementations. Thank you.
That's it. Thank you.